I would like to thank the organizer for this nice workshop with plenty of different talks with each his own flavor, so it's very nice workshop. So I will address some questions about the kind of relation that can satisfy a function, and I will be first of all interested in trying to decide if a function, which is a power theory, is or is not holonomic. So the analytic strategy consists in showing that the function does not fulfill some regularity criteria that a holonomic function has. So for instance, an holonomic function, a function that satisfies a linear differential equation, has a finite number of singularities. So if you succeed to show that the function you are interested in, your spatial function, has an infinite number of singularities, then you're done. And it was a strategy to show that generating series for quarter-plane walks are non-holonomic. Then you pick up one particular singularity of your function and you propagate it into an infinite number of singularities by using a certain group action. So what you can also check is that your spatial function has not a good asymptotic. So for instance, an holonomic function has, this kind of asymptotic that was succeeding. And you can show that the generating series for integer partition has bad asymptotic, so it's not an holonomic function. Well, when you have done this work and you know that your function is not holonomic, well, you can ask if it has some other type of differential relation. So now you can wonder if your function is differentially algebraic, that is, it satisfies a nonlinear differential equation. And in that case, the analytic criteria will not be sufficient. And in fact, it's due to the fact that the differential algebraic function is a very wide class. So for instance, any kind of things can happen. So if you check the singularities, the theta function, which is a differentially transcendental function, has only one single pole. And the partition function is differentially algebraic and has an infinite number of singularities. On the other side, you have bound on the asymptotic of the coefficient, but it's a very large bound and it's difficult to use. So I would like to find some kind of methods to tackle this situation without really using analysis. So in many cases, we will use some extra information on the spatial function, and this extra information is that it satisfies a discrete equation. And for instance, if you are looking at some generating series attached to a p-automatic sequence, it satisfies a linear p-Malar equation, where you have the dynamic which is given by the exponentiation of the variable by p. For generating series counting walls in a quarter plane, then you can relate this generating series. There are three variates, so I don't know why I put a z, so there's no z. You can relate them to function in one variable that satisfies, depending on the case, in genus 0, so I will explain this later. So they satisfy Q difference equation, which is of order 1 and non-homogeneous, and with rational coefficient, and a genus 1, it's a finite difference equation, always of order 1, whose second member is this time an elliptic function. So they are very simple discrete equations. So knowing this, the algebraic strategy will consist in using the form of the discrete equation to find constraints on the type of differential algebraic relation that the function satisfies. So I will just give you a baby example, very down-to-earth example. So you take the Q logarithm, which is the log derivative of a theta function. So it satisfies this rank 1 non-homogeneous equation, and you want to show that it's for instance, transcendental over the field of rational function. So how do you do this? You suppose to the contrary that it is algebraic, and you pick up a minimal polynomial relation. So this n is minimal. N is strictly positive. So then you use the dynamic of your discrete equation by changing x into qx in your relation, and you use the form of the discrete equation to plug it in this new relation to find a new algebraic relation for the q logarithm. Then you can eliminate qx to the n between these two relations to find an algebraic relation of order strictly inferior to your minimal relation. So by minimality, this algebraic relation must be completely trivial, and it means that all the coefficients must vanish. And especially the first one. And the first one tells you that you have to find a rational fraction such that it's transforming q minus itself, it's a non-zero integer. And then you just check easily with degree of rational function that it's not possible. And you find a contradiction. So this is absurd. So just a note is that, well, okay, if you have such a relation on the coefficient, then you can get some relation on the function. So if you rewrite this relation and you just say that minus n, it's minus a times 1, and then you use the functional equation for the q logarithm, then out of this, you get that a certain function is fixed by x goes to qx. And this tells you that if it's algebraic, the q logarithm, then it must be some rational function plus an elliptic function. So when you have, you know that there is a relation, you can read it through the coefficient, and then you can go back and deduce a certain relation on the function. Well, so the Galois theory of difference equation, which is a discretization of the Galois theory of differential equation of Picard and Vessieux, systematizes this naive elimination process. In fact, out of the structure of the equation, we get an algebraic group whose structure encodes the algebraic relation between the functions. So, first of all, it's the goal of this series is to determine the potential algebraic relation for the series. So it's, for instance, if LQ of x is algebraic, the relation is of this type. And then it tells you what kind of algebraic constraints you must have on the coefficient of the equation in order to acknowledge the relation on the function. And this is what we found for the Q logarithm. Now I won't enter into detail on the Galois theory. I will just give you Galoisian criteria. So I'm in a very mixed situation. So I'm considering a field with 3 operators, an automorphism sigma, and 2 almost commuting derivations. So I'm just requiring that the Lie algebra generating by this guy is, or the Lie commutator is just a constant for the automorphism times this derivation, and I'm also requiring that my derivation are commuting with sigma. Now the Galoisian criteria is as follows. So I have the sigma delta base field, and I take an element B in K. So I suppose that I have found a solution of my equation sigma of f equals f plus b in some field extension of my base where I can derive with respect to the 2 derivation. And I assume that the constants for the discrete operator form an algebraically closed field. Then my function f is differentially algebraic over k if there are some integer r and s and some constant for the discrete operator, not all 0, such that this linear differential equation is some kind of cocycle with respect to the discrete operator. So I won't prove this Galoisian criteria, I just want to explain how it can be deduced for those who know a little bit of Galois theory. So you are using the commutation of the operator sigma with the derivation to derive this equation and to find an whole bunch of rank 1 non-homogeneous new equation. So if you have a relation for your function and its derivative, an algebraic relation, then it means that you have an algebraic relation between the solution of all these equations. And when you look at all these equations, the Galois group is a vector group. It's a subgroup of the vector group, and you know that the algebraic subgroup of vector group are vector spaces. And that's why morally you get a linear condition on the coefficients.
So this is just an if?
So I come to the only if. So the only if is as follows. So if you get such kind of relation, then when you plug in f, it means that this guy must be a constant of your field of solution. It's exactly what happens to the Q logarithm. So the Q logarithm is a meromorphic function of a C star. And what you can deduce from the relation between the coefficients is that the Q logarithm minus a rational function is an elliptic function. That is a new constant. So you, in order to get the other direction, you need to have control on the constant in the field of solution. So otherwise, if you don't know the constant of the field while you are solving your discrete equation, then you will be in trouble. Okay, so now I will explain how we can apply this to walks in the quarter plane. So a walk in the quarter plane is a sequence of points with integer coordinates, such that when you obtain one point from another by a prescribed choice of direction. So I give you an example. So if you just enumerate what kind of possible choice of this, you have a very big number of possible choice. And when you make a refined study and you avoid trivialities and you use symmetries of your set of direction, you have only 79 interesting cases. Okay, so in combinatorics, people want to count such kind of objects. And you encode a walk with a set of direction, which is encoded as a pair of integers between -1 and 1. And you can choose also to put weights on the direction. Here you choose to get a probability to go in such and such direction. To such an enumerative object, you associate a generating series as follows. And in fact, here, this variable t counts the number of steps you have to do. So you can show that this trivariate generating series satisfies a functional equation of the following types. So up to now, there are no dynamics in count. So I put in blue some object because it's very spatial and central in this study. It's a biquadratic polynomial in x and y, and it's called the kernel of the equation. So the classical strategy was were as follow, and this is still our strategy, is the equation is quite complicated, written that way. But if you make this term vanish, then you have decoupled your variable x and y, and it's a much simpler situation. So we want to study what is the zero locus of this guy. So, the zero locus is called the kernel of the walk. So in order to avoid stupid things, I choose my t that I see that as a parameter, as a real number, which is not algebraic of a Q. I don't want that my zero locus degenerate all of a sudden, so I avoid this thing. So looking at the zeros of my kernel in P1 times P1, in fact, I have a trichotomy. So either this kernel is reducible, and from a combinatorial point of view, the generating series is very simple, or it is an elliptic curve of genus 1, or it is a genus 0 curve with only one singular point. So this is where this genus 1 and genus 0 appears. So I won't talk about the first case. I will concentrate about in the second and the third case. Okay, so now what is the dynamic? So the dynamic is as follows. Since you have a biquadratic polynomial, you can build on two involutions of your kernel. The first one is just taking a point and you find the other point by fixing the x coordinate, and the second it moves on only in the y coordinates. And if you compose these two involutions, you find an automorphism of your work. So this automorphism is very special and one has to study it. So now you, just to recall what were the previous results, for the 79 unweighted work, when the group of the work, this group generated by the automorphism is finite, so it happened for 23 works, then the generating series was shown to be algebraic or holonomic. When the group is infinite, then it was shown that the generating series is not holonomic. For 51 works, the genus is 1, and it's the work of Boston, Korkova, Rachel, and Salvi. And, Irina, Korkova, and Rachel really put this in an analytic framework. And for the 5 remaining work of genus 0, it was done also case by case. So no one could ask, when the series is not holonomic, is it differentially algebraic, and what happens if one put weights in all this stuff? So no one can, in fact, characterize all the genus 0 case by putting weight. So if you're fixing a real number which is in this interval and not algebraic of a Q, then you can show that, in fact, all the genus 0 works are supported by this set of direction. And the singular point is 0, 0. And in that situation, you can parameterize your kernel by birational maps, such that outside the singular locus it's a bijection, and you can do it in a way that it preserves all the dynamics on the kernel. And now, pulling back the automorphism of the work, it's a multiplicative automorphism of P1, and you can almost explicit Q, because you have an indeterminacy, you don't know if you compute Q or 1 over Q, but nonetheless you can show that it's a real number, not plus or minus 1, and that depends on T. And in that case, since it's not plus or minus 1, you know that the group will be always infinite when you're in genus 0. And then the idea is that you will pull back your functional equation from the kernel to P1. So you do this as follows. Just for ease of notation, I define this F, which is just the kernel times the generating series. So any algebraic properties on this F will be the same on Q, because you're just multiplying by some polynomials. And the generating series is shown to be convergent on this open. So is F. So you can use your kernel equation and then just look at it on the kernel. Sorry, the functional equation, look at it on the kernel. So if x and y are in the kernel, then x and iota 1 of I are of it, and then you can subtract, and you find an equation that involves only this function and some transform of this function. Then you use your parameterization, and if you denote by f of omega, the function f composed with the parameterization, at the end you get a Q differential equation of order 1 with a second member that is a rational function, which is as follows. Okay. So then you are in an algebraic framework, and my field C of omega with this Q difference operator and this derivation is a sigma delta field. Both of these guys commutes. You can also show that the function f is d over d omega transcendental over the rational function if and only if your generating series is d over dy transcendental, essentially because you pass from one to another by composing with a rational function. And then you have this very easy rank 1 non-homogeneous differential equation. Okay, for the genus work, well, the uniformization is much more tricky, and it's the work of Irina Krukova and Kilian Rachel. Then you can parameterize your kernel via torus, and you can show that composing with this parameterization, you end up with this finite difference equation, whose second member is an elliptic function. And now if I denote by CE the field of elliptic function, I'm once again in this algebraic framework, just by considering this shift by omega 3, the derivation d over d omega, and since I'm composing with elliptic functions that are differentially algebraic, I know that my small f is d over d omega transcendental over the elliptic function, if and only if the generating series is d over dy transcendental over the rational. Okay, so I just can apply the Galois theoretic criteria to show that if the generating series is differentially algebraic, then in genus 1, I must have a linear equation with constant complex coefficient in B, the second member, that is equal to this cocycle. In genus 0, the same thing. I have a cocycle of this form, and G here is a rational function, and here is an elliptic function. Okay, such kind of equation, so we call them telescoping equation because it reminds us to telescoping problem where you have two derivations in x and t and a function f in x and t, so that you're asking, given f in x and t, can I find a derivator in d over d, a linear differential operator in d over dx, such that applied to this function I find the derivative of another function with respect to t. And here it's a sort of discretization because you're just looking at a cocycle instead of a closed differential form. Okay, so now all the point is showing that such an equation cannot exist. To do this, we use a strategy that has been created by Chen and Singer to tackle this kind of problem. So you can show that if you take Q, not a root infinity and a rational function, you have an equivalence between the following. So you have a telescoper for B, and in fact, it's equivalent to, you have a telescoper of order 0 for B. And this last condition can be translated into a condition concerning the residues of the poles of B. So what is called the Q Orbit Residues. So I won't enter into a very precise definition of what this is. I will just give you an example. So you expand a rational function, and you see that in my example, the rational function are only poles in 1 and 1 over Q. And these two guys are on the same Q orbit. So what is the Q residue of 1, of order 1? It's just this coefficient, 1. But the Q residue of 1 of order 2, so we are looking at higher residue. So there is a non-canonical question in this definition. Then it's minus 1 plus 2, and it's equal to 1. So you just sum here these two guys. But doing this, you have taken into account a precise choice of the uniformizer at these places, at the places 1 over Q. So this definition depends on the way you choose your uniformizer at the pole. And it will be really important in genus 1. So now, as a corollary of the result of Chen and Singer, you know that if a function b has a pole of order m such that there is no other pole on the Q orbit of omega 0, then you cannot have a telescoper for this function. And you reduce the question of existence of telescoper into a very simple question showing that you have an isolated pole on its orbit. So the strategy is as follows. You want to prove that the generating theory is differentially transcendental, so you suppose the contrary. And then you go to a much nicer setting by using a parametrization of the kernel and reducing this question to show that a simpler function is differentially algebraic. Then via the Galois criteria, this question of differential algebraicity reduced to a question of existence of telescoper. Finally, if you use the residue criteria, you perhaps have to show that the function has only one pole that is isolated on its orbit. And then you are done. You have proved that B has no telescoper. Okay, so in genus 0, everything works very well. And you can show that for all the genus 0 walks, the generating theory is differentially transcendental. So how does it work? So generically, your function, the one you are interested in, you can look at it in P1 times P1, and you can show that it has 6 simple poles. None of these guys are the singular points, so you can pull them back uniquely on the side of P1. And the end of the proof, for instance, you find some omega 1, omega 2 that goes to P1 and P2, and you show that they are not related by some power of Q. And to do this, you use the fact that Q depends on T. And you use that the transcendence of T over Q bar to compare the degree on both sides of the equality. Okay, in genus 1, in fact, the situation is much more tricky. So for genus 1 walk, the following are equivalent. The function is differentially algebraic. This elliptic function has a telescoper, and every orbit residue of your elliptic function is 0. So the definition of the orbit residue is a bit complicated. I won't detail it, but it's the same spirit than in genus 0. But this time, the orbit is with respect to the addition by a prescribed point on the elliptic curve. So first of all, you want to gather the poles of your function into orbit with respect to addition by a certain point. It appears that if you are in this algebraic setting, you can easily compute the point without using the parametrization, which might be highly transcendental. So you can compute the points by which you are adding to get the automorphism of the walk, and you can also test if your automorphism of the walk is finite, because it's equivalent to the fact that the point is torsion on your elliptic curve. And something that is hidden in the t variable, that is, in fact, you can consider t as a parameter, and instead of having one elliptic curve, you have an elliptic surface. And so you can use machinery of 8 to decide if 2 points are related into an orbit. So for instance, if you want to know if x1 is sigma n of x2, then it's equivalent to this thing. And this can be decided because then you compute the 8 of x1, the x of x2, and you are checking such kind of relation. And you have a bound on a possible integer n, and then you just compute it thanks to the computer. So I went very fast. Okay. Sorry. This is not what we have done. In fact, we have done all the computation by hands. And in fact, we have used a Galois action on the field of definition of the kernel to understand in which cases we have or not the nullity of orbit residues. So we have done the following. So remember that we have 51 cases where the genus of the curve is 1, and where the group is infinite, and except 9 exceptional cases, all the generating series in the unweighted situation are differentially transcendental. And in the 9 exceptional cases, it happens that the function we are interested in has a telescoper, and so the generating series is differentially algebraic because you can control the constant in that situation, but we can show that it is not holonomic. So just as an example of what can happen in that 9 exceptional cases, in fact, in one case, the divisor of the function we are interested in is very simple. It has only simple poles that are all on the same orbit. So the orbit residue is just the sum of the residue. And we know it is 0. So we have studied these 9 exceptional cases by just doing this kind of computation. And there are also some symmetries between the residue of the different poles using some symmetry of this function. This function B satisfies iota 1 of B equals minus B. So you can find some relation between the residue. Okay, so anyhow, if you want an explicit differential equation for the generating series, it's something that has been done by Mireille Boscamelo, Olivier Bernardi, and Kilian Hachel by using a different method and not using these telescopers. Because until now we are not able to give really explicit differential equation. And some part of this result of this theorem has been extended to the weighted cases by Thomas and Kilian. Okay, so I just want to show you an example about what is the strategy with the Galois action. So for instance, you consider this set of direction and with weight 1. So the kernel is given by this equation. And we have reduced the question in showing that the function generating series differentially algebraic if and only if this guy has a telescoper equation. So there should be a square here. It's a square of this guy. So this cannot happen because if you compute the poles of x iota 1 of y minus 1 in P1 times P1, it gives you this guy, and one of these is isolated on its orbit. So how do you show this? So you use, for instance, a complex conjugation, but you can take any Galois action on the base field. And since everything is defined above Q of t, the Galois action commutes with the addition by a point. And now I claim that the orbit of infinite I as a pole is just made of infinite I. So the idea is as follows. Suppose that infinite minus I is some iterate of infinite I. Then infinite I is a complex conjugate of this. Then you use the orbit, you exchange these two, and at the end of the day, you find that infinite I is fixed by some iterate of your automorphism, which is a contradiction because we have supposed that our automorphism is of infinite order. So in most of the cases, we have used this Galois strategy to conclude that you cannot have a telescoper. Okay, so now we'll talk about work in progress, about the t derivation. So by choosing t as a complex number, so we were not able to derive with respect to t. And we might be interested in understanding what are the kind of relation in the t derivation of the generating series. So now I will pass to an ultrametric setting, and I will define a norm on q bar of t by looking at the variation at 0. And I consider this derivation, and you can easily show that you can find an algebraically closed field that is complete with respect to some extension of the norm and has also a t derivation. And then it happens that everything passes to this framework. So you can uniformize in genus 0 and find a prolongation of your generating series that satisfies a Q difference equation of the same type. And I don't know if you remember, Q was depending on T, and in fact it has a pole at 0, so and it has models strictly greater than 1. Now, the Galois theoretic framework is a little bit intricate, more complicated. So you considering as a base field the field of elliptic function with respect to Q, and you're adding the Q logarithm. So why are you doing this? And this is because you can build on a derivation with d omega and dt and the Q logarithm that commutes with the Q difference operator. And this is more or less a kind of Gauss-Manin connection on the curve. It's a way to see this. So now you have two derivations, one with respect to omega and one that combines omega and t. And you can show that the generating series is dy and dt algebraic over the field of rational function. Then your function f is differentially algebraic with respect to this guy. Okay? So now the Galois criteria tells you that you must have a linear differential equation involving the two derivations. Yeah?
So can you show again the previous one? So what do you mean by being dy dt?
So since this commute, you have an algebraic relation between so it means that you have an algebraic relation over C of y and t between dy or dt s of your function, big F.
Okay, so it's not asking that it is dt algebraic and dy algebraic, it's much weaker.
It's stronger.
No, it's weaker. So it's so fast as to have some PD to be algebraic, the algebraic in more sense.
If it's satisfy a differential equation in only in T, it's differentially algebraic in myself. My sense. Perhaps I missed the question. Yeah, in EPD. Okay. Okay, so you reduce to the existence of such telescoper. And I remind you that B, in fact, it's a rational fraction. And G also, it's a rational fraction. And the miracle that happens that, in fact, if you add such equation, then you can make a descent and show that you must have a telescoper that involves only omega. And we know that in genus 0 it's impossible. So I just, detail it a bit, the descent, it's a little bit more technical. So remember that my derivation, big delta, is as follows. And I just show you at the beginning of my talk that LQ is transcendental over CQ of omega. So now we can easily show that since B is a rational fraction, if you derived with respect to big delta I times, then the highest term in LQ is this guy. So now if you write a telescoping relation in these two derivations and you're chasing from the highest power of LQ, with a little bit work, you can show that it gives you a non-trivial relation of this type. So it's quite strange, but you end up by saying that this differential transcendency 2 derivation reduced to showing that there is a differential transcendency in 1 derivation. It's just because the second member is very simple. Okay, so to conclude, I'm really early, they will be very happy. So what I tried to convince you that, in fact, when you have a nice functional equation, you can combine it with Galois theory to find criteria for differential transcendence that are quite easy to check via telescopes. And this existence of telescopes is equivalent to some nullity of orbit residues. So this, then you can wonder if the computation of orbit residue will give you a telescope, and this is essentially our hope. And for instance, in genus 1, it will be equivalent to build on an elliptic function with 2 prescribed singularities. And this is something that can perhaps be done. Okay, so this is what I have done. We are really interested in finding an effective procedure to produce the telescope and compute the orbit residue. But in the case where you are interested in the derivation in y and the derivation in t, the form of the differential equation in d over dt is still mysterious out of the telescoping equation in x. So we really need to study a little bit more this telescope to understand what kind of differential equation you can have in the t variable. So I will end my talk here. Thank you.
Yeah, so say in the genus 0 case, so you proved that if there is PDE, then there should be also a differential equation just in dy.
Yeah.
And since there's not, okay. Can you say something about this series, say, Q evaluated at y equal to 1? Is it?
No, you cannot go in that direction. If the function is in x, y, and t is differentially transcendental, it may happen that you may have a differential algebraic relation. And even if the function is differentially algebraic in the 3 variable, it may happen that you cannot specialize your algebraic relation at x and y equals to 1.
And your last sentence, so it refers to the genus 1 case, because that's the only case where you have telescopes?
Yeah. So we are in the process of having the same result in the genus 1 case. It happens that in the genus 1 case, the invariant of the elliptic curve is non-integral, and you can parameterize with the Tate curve, which is a multiplicative version of So you can parameterize like this, and you will have a situation so that you have 2 Q. One is for the elliptic curve, and the other represents the automorphism of the walk, such that here you have a function which is elliptic with respect to your curve. So the descent process is a little bit more demanding, but it works. It's only, well, the uniformization, one needs some care, but it should be okay. So the same. So if your function is differentially algebraic, you're generating theory in dy and dt, then you must have a telescoper only in the omega variable.
Okay, so I got a working microphone now, and so you want to have it?
You mentioned that you were able to solve whether or not it was differentially transcendental for the unweighted cases, and I was curious as to whether or not, if you can put in weights, and if that will carry through calculations, and you can figure out if there are some breakpoints for the weights, whether it will switch over, or whether weights don't actually change whether or not it's going to be differentially transcendental.
Yes. So in this 9 exceptional cases, well, it's computation with computers, so we can show that, so we think we have an example where you put weights on cases that was differentially algebraic, and then you break up the orbit. So just using the 8 computation, there are no more in the same orbit, and you cannot have a telescope, so it becomes differentially transcendental. You can imagine that the same things happen for differentially transcendental cases, and you put weight, and then it has a telescope, they go in the same orbit or something like this.
Further questions?
In this walk problem, you have nearest neighbor walks corresponding to a biquadratic kernel, and biquadratics are well known to be elliptic curves. How about more general walks where maybe you have the next nearest neighbor walks and a bicubic kernel, which is not going to be an elliptic curve anymore? And so the symmetry, the group, which is crucial, finite or infinite, will be systematically, the birational symmetries will be finite generically. There are a few elliptic curve, biquadratic that are elliptic curves, but generically you are not, you're a higher genus. But that's, everything will be the same. That's simple generalization.
No, no. No, in fact, it's all of a question. So when the cases of higher genus corresponds to bigger steps, so if you have noticed this work, they have only, they going to 1 in just step 1. And if you put step 2 or step 3, then you end up with a higher genus curve. And as you know, this group of automorphisms is finite. So I think there are work from Mireille and Lin where they are able to get some automorphisms that are infinite order. So it's very puzzling, but they are going out of the curve. So there might be some strategy to go out of the kernel. In fact, perhaps to, I don't know, to the Jacobian, or well, to get the same strategy. Yeah.
As I said, there are bicubics that are elliptic curves, so you might be for this next next nearest neighbor walks, 2-step walks, and whatever you call it. You could be still with elliptic curves.
Oh yeah, if it's biquadratic, it's yes, either genus.
No, but bicubic. There are elliptic.
Yeah, okay. Oh well, you have some singular point. Okay, okay, yeah. Yeah, if it's an elliptic curve, it's okay. If it's higher genus, our strategy does not work. But we can dream that in 3-dimensional work, it will work again with K3 surfaces, but it's a lot of work.
Other questions? If not, then thank you very much again.